In this screencast, we're going to perform an integral momentum balance on a specific system shown here, where we have a T attached to a pipe that splits an incoming water stream into two free jets. The exit speed of both streams is 30 feet per second. We're going to neglect any viscous effects within the pipe and the T, and also neglect gravity. And what we're interested in determining is the X and Y components of the force that the pipe exerts on this T. So the first thing to start with any problem is with a figure, and we have one here, and so we just want to double check that everything's labeled appropriately, and we see that our velocity coming out of both parts of the T is labeled as 30 feet per second. We're given areas of both ends, and we're given the area of the incoming end. So the second thing in performing a momentum balance is to determine what our control volume is going to be for this system. So let's go ahead and draw that out. Now I've drawn this line here just to indicate we do have a T attached to a pipe, and so we're going to choose the T as our control volume. So I'm going to just draw in red around the control volume of interest. And we need to rewrite what we are looking for. So I'm going to say find, we want the force in both the X direction and the Y direction of the pipe on the T. Alright, so a good place to start with this problem is to write our general equation for performing a linear momentum balance on the T. So we know that the differential with respect to time of the control volume is the velocity times the density times the change in volume plus whatever enters that control volume through its control surfaces, and this is the velocity times the density times the velocity dot product with the normal over the area that it enters, and this must be equal to the sum of all forces acting within the control volume or on the control volume. And this must equal the sum of the forces acting on the contents of the control volume that we've designated here in red. At this point we would list our assumptions, and we're going to say that it's steady state, the flow is steady state, so this allows us to get rid of that first term, the rate of change of the momentum of the contents of the control volume. So we're left with just that second part of the equation. So let's work with that side first. So if we're interested in only the X component of the momentum equation at this time, we could rewrite this. So let's go up to our figure as we do this and label a couple more things. First of all, we're going to say that this into this control surface, this is control surface 1, we'll call this control surface 2, and we'll call this control surface 3. So for the control surface at for control surface 1, we have momentum entering our control volume, so we'll have negative V1 times the density of the fluid, again times V1 and area of 1, and so that covers this region here. And for momentum leaving out on the other side is going to be positive. We'll do the same thing, but this time use the velocity at 2, rho V2 A2. And we don't have to worry about the control surface at 3 because that's only in the Y direction, and right now we're only concerned with our X components. So now let's work on the right side of our momentum balance equation, the sum of the forces. We have our pressure force acting on section 1, and this is, if we work in gauge pressures, we'll say that this is P gauge at 1 times the area at 1. And since at section 3 it's open to atmosphere as a free jet, there's going to be no pressure force at that point, so the only other force would be that of interest, which we'll say is Fxp for the force of the pipe on the T. And this force, if we looked up at our diagram, would pretty much be the anchoring force that the pipe is exerting on, holding onto that T. So all said and done, if we put these two together, we get the following equation. So to determine the force, we need to look at our diagram and see what we have. Since we're working with water, we know the density. We're given the velocity at 2 and the area at 2. So we would know that first term. We have the area at 1, but we don't have the velocity at 1. So V1 would be unknown. We also, as we say, we have the area at 1, but we are not given the gauge pressure of the pipe. So we would also have to determine that. We don't have the gauge pressure of the water at point 1, so we'd have to determine that. So we could use the continuity equation to determine V1. And this basically says for an incompressible fluid that the volumetric flow rate coming into the T must be the volumetric flow rate leaving the T. So we could rewrite this as the area at 1 times the velocity at 1 equals the area at 2 times the velocity at 2 plus the area at 3 times the velocity at 3. Since we're interested in V1, we could rewrite this as the following. So now we have a relationship for V1. So the other variable that we are interested in is this gauge pressure at 1. So we need a relationship between the pressure and the velocity of the fluids. And we could go back and estimate this gauge pressure using the Bernoulli equation for flow between point 1 and point 3. Point 2. So writing the Bernoulli equation, we see that the pressure at the control surface of 1 divided by the density of the fluid plus the square of the velocity at that point divided by 2 must equal the same at another point, which we are going to say 0.2, so that we could get rid of the height term. And we know all the values here except for the gauge pressure at 0.1, so we could solve this. So now we have three equations. Our first one, the one that gives us velocity at 0.1, and the one that gives us the gauge pressure at 0.1. And so we could now solve for the force in the x component, the force in the x direction. So plugging in numbers. Now if I plug all these numbers in, I get a velocity v1 equal to 18 feet per second, and a final gauge pressure at 0.1 equal to 558 pounds per foot squared. Now one thing I want to point out is the units that we're using. Since the density reported is in slugs per feet cubed, we need to convert this to our pounds force. So just a reminder here, that's why I have this arrow. Our pound per square foot is the same thing as 1 slug per foot second squared, because the conversion is that 1 slug times 1 foot per second squared is the same thing as 1 pound force. So just a reminder when we're using these types of units. So now we could plug these values into our first equation that we had up here to calculate the force in the x direction. So let me rewrite that. So here I have our final equation to calculate our force. I've plugged in all the numbers, and when I calculate this, I get a force of negative 4,880 force. So since our force is negative, what does that imply? We have our water flowing into our T from left to right. And when we declared our nomenclature for this system, we said that positive y was up and positive x was to the left. So a negative force means that the force acting on the fluid is to the left, meaning the force of the fluid acting on the T is to the right. If the anchoring force wasn't here, so if this force wasn't there to hold that T in place, then the force of the water acting on this T would just shoot it off to the right. So that's what our negative force implies, the force required to anchor that T in place. Now let's work through the y component of the force. Now for the y component of the force exerted on by the pipe on the T, we use the y component of the linear momentum equation, which is pretty straightforward. We look back at our diagram, and the only component we have moving in the y direction is at the control surface 3. So pretty much the force in the y direction is going to be equal to the momentum leaving the system, and we don't have any pressure force in the y direction because at control surface 3 it's atmosphere, and there's no pressure acting against this control volume in the y direction. So we could write this as the velocity at 3 times the density of the fluid times the velocity times the area must be the force in the y direction. And we could plug in some numbers. We have 30 feet per second. We're going to square this times our density of 1.94 slugs per foot cubed, and our area of 2 feet squared. This gives us a force of 3,500 roughly pounds force. And because it's positive, it's acting in the y direction up, which means that the force the pipe is acting on the T in the y direction is upwards. So hopefully this gives you a good idea of how to calculate a momentum balance using the integral method. So hopefully this gives you a good idea on how to use the integral method of the momentum balance to determine the forces on a system, to determine the forces in a control volume.